but they'll be rolling in over the course of the next 5 to 10 minutes probably.
Awesome.
Okay, I'm going to go on mute.
Cool. We'll just give it a minute or two and then we'll get going.
Sounds good.
All right, well, it is 5:30, so we'll get started. Cool, so thank you everyone for joining. If you were here last week, thanks for joining again. If you are new to the Data Science Development Series, I'll just give a quick overview of what the purpose of this program is and what we are here to do. So Data Science Development Series is a 6-week free learning experience for all the core concepts of data science, right? Last week we started with just machine learning 101. This week you're going to be able to get to understand computer vision, and that's right, isn't that? Oh, computer vision is right on the screen. Next week we're doing deep learning. We have natural language processing after that, and then we're also going to be able to do work on recommendation, moving forward, recommendation engines as well. So we have a good series, ready to go for the next coming weeks. It's going to be every Wednesday at 5:30 to 7 o'clock. So, make sure that you come back after this if you enjoy the content. But like I said, this episode is going to be on computer vision. I'm Brian O'Connor. I am the data scientist lead at Pandera Systems, based out of Orlando, Florida. I'm actually in Boston. For those not familiar with Pandera Systems, we're a data analytics consultant firm. We're going to be sponsoring and hosting these data science development series each and every week. So I hope you guys get used to this face. That doesn't even look like me now. If you notice, I got all this long hair now, but that's an old picture. Anyways, the sponsors of this program are, like I said, Pandera Systems. We have TAB, which stands for Tech and Beer. That is a community organization where they set up events for the community to meet up and do some sort of events and talk about technology, grab a drink somewhere. And other sponsors, Southern Data Science Conference. So Southern Data Science Conference hosts annual conferences and a bunch of other events throughout the year that are really good in the data science space for you to learn. Now, you can follow us on social. Before I introduce Matt, I do want to say that this is our second week, so we are learning how to host these. Last week we had over 400 people join, which is incredible. Except that means just there was a lot of questions coming in and chats. So one thing that everyone should know beforehand is everyone's going to be muted. So don't worry about accidentally speaking. We have you automatically muted. Second is all the content that Matt will be presenting is going to be shared after this later tonight or tomorrow morning. So that will include any type of content or code snippets or whatever was gone over today. That will be shared via email, including the recording of this development series, right? So expect that. Any type of questions that you do have, please use the Q&A section. So you'll see in Zoom here, there's a double chat window icon with Q&A underneath it. Now, what happens there is if you type in Q&A, please use this for any questions you have related to the content. So if Matt is, he delivered it, he was talking about some computer vision problem and you didn't understand it and you want to follow up on it, you could use the Q&A, to post that question in. So what will happen is I'm going to be monitoring the Q&A window, and anytime that there's a question that we might want to interject Matt and he could answer kind of in the flow of his presentation, then I'll make sure to stop him when we get answered. If not, we're either going to leave the question towards the end or when there's or else I will answer the question by typing the answer to you, and then you'll be able to receive the response. So that's for you doing Q&A. I will say, and I see people already kind of in the chat, there's also a chat feature in Zoom. So any, socializing or, letting people know who you are, what type of job you do, where you're from, like we could do that all in chat, right? It could just be conversational throughout the entire presentation. But like I said, any specific questions related to the content, just put those into the Q&A session, and we'll make sure they either get answered by Matt himself or I will be doing answers via chat. Cool. Well, with that said, let me introduce Matt Hagan, who's data scientist at Home Depot. Great.
Hey, Brian, thanks a lot. And Tommy for hosting this. It's super exciting because I know it's definitely, tough to go to conferences right now. And this is really a great outlet to, if people are interested in learning more about a certain subject. I'm sure there's a lot of people out there that, this might be their first time hearing about computer vision, and then there might be other, deep learning practitioners. So I wanted to try to create a presentation that won't be, too deep, where if you're just kind of starting out, this can kind of give a good introduction to computer vision, but then maybe also talk about a few advanced concepts as well. If you're a data scientist in computer vision, maybe there'll be a few things in here that are maybe things you haven't heard of, or maybe new to you. Let me share, and with that, let me share my screen to start the presentation. A little bit about me. I know we only have an hour. I started off kind of as a database engineer at Turner Broadcasting. We worked a lot with video games there, and it was super fun. I was like mapping different controllers to all these classic games to make sure you could play Pac-Man, right on your PC, or Sonic the Hedgehog. And it was kind of a dream job in a way. But, you can only do, in a way, with database engineering, it's super fun. But, with the Netflix prize coming out and learning about patterns and trends, I just felt like there was only so much work you can do with moving data from place to place. You can get really creative with it and work on, making it faster and more efficient. But, when that Netflix prize came out, that was it for me. I just really loved the idea of trying to find patterns and trends, and being able to, come up with different algorithms to try to create, more predictions. And I guess just the word AI just really just got really exciting for me. Let me share my screen real quick. So then after I was working at GameTap at Turner Broadcasting, I decided to go back to get my PhD, and I did that in bioinformatics with biology and computer science, trying to merge those two together. And then after that, I did a startup for a little bit, and then this opportunity happened at Home Depot, and I've been there for 4 years now, a senior data scientist on the visual intelligence team. We just had a lot of success with, we had this cold start problem where we have so many new users coming to Home Depot, and we also have so many products that are constantly being onboarded, that a lot of the traditional recommendation algorithms really weren't working as well. Because for Netflix, you go onto Netflix, and you only have so many movies, and those movies stay there for a while, and you have a lot of repeat users. So we wanted to see how well a content-based visual similarity algorithm would work. And when we built that, it just did so well that we decided to form our own visual intelligence team. And it's been great the last 3 or 4 years, and that's kind of was my introduction to kind of getting heavy into computer vision. So I've been practicing it for 2 to 3 years. I'm going to share my screen right now. Share the desktop. Uh-oh. It says it's not allowing Zoom to share my screen.
Hold on, let me looking at let's see, all panelists. You should be able to share. All panelists can share. All panelists can share. You should have permissions. What is it telling you exactly? You don't have permissions, or you just?
I think maybe now I was just given permission. Let me try and share it right now.
There you go. It's going.
You got it? Awesome. So Actually, maybe I could just share my whole screen because I'm going to be switching back and forth between the PowerPoint and the code. Okay, can you see the PowerPoint?
Yep.
Yes.
Okay, awesome. So this is, as Brian was saying, this is session 2 about computer vision. And here's just all the different sessions that we have going on. We're gonna have session 3 will be Nick, who will talk more about deep learning. But this is, I'm actually going to talk a little bit about deep learning in this talk as well, because computer vision's kind of an older field that's been around since it's really started, I guess, to take off maybe in the early 90s. But when we started applying deep learning with computer vision, the levels of success just like increased by orders of magnitude. So I want to kind of divide the talk into 2 parts of just the traditional techniques that started in the 90s, and then all the way up to maybe the beginning of this decade, 2010, 2012, is when deep learning really started taking off. And, it's funny, actually, deep learning was, it became really popular with, when it was kind of rebranded. Data science, actually, I bought a book on data mining. I was kind of embarrassed to show people this book because I found it so interesting, all the concepts they were talking about, but it was kind of a geeky name. And then they rebranded it to data science. And now, like, everyone's all about it. And it's kind of the same thing with deep learning, how, neural networks were, pretty successful, but they weren't really that as well adopted. And then, they rebranded it to be called deep learning. And then NVIDIA started creating really powerful GPUs. And then that whole field exploded. But I'm going to kind of start off to talk about the traditional techniques in computer vision before deep learning began. And I'll talk about image filtering and feature descriptors. And these are the 2 main areas that had a lot of success with traditional computer vision. And then I'll start to talk about deep learning, which is actually using neural networks for a lot of these tasks with images, with classification, with object detection, and with segmentation. So here's a lot of the books I'm going to provide a lot of code snippets. And a lot of the books where you want to read more about those code snippets were kind of adopted from these 4 books. These 3 right here are more the traditional computer vision techniques. And the last one goes pretty heavy into computer vision, or pretty heavy into the math with deep learning. That's an exclusive deep learning book. So the first 3 books uses this package called OpenCV. Highly recommend that. It really kind of depends on what type of, what your goals are, because if in the business you can be, working for different companies, you can be super successful, utilizing these packages, writing code in OpenCV, and it can work out really well. But, a lot of people like to get, more traditional textbooks and learn all the math behind it. So it kind of depends, whether you want to read the papers or just kind of look at the code of how to implement these techniques. So what I'm going to try to do with this session is kind of give both examples where I'm not going to review the equations too much, but I'll still show the equations so you can kind of, when I share these slides, you can kind of see the math behind how these techniques work. And I'll also give examples of the code. So for deep learning, you can actually use deep learning in OpenCV, but it's a little bit harder to alter. It kind of comes more out of the box. If you want to build your own deep learning code, then the 2 largest packages right now are TensorFlow and PyTorch. So I'm not sure, how many people have been exposed to that, or if everyone's very familiar with that. But TensorFlow and PyTorch are pretty huge right now. There's other deep learning packages out there for you to quickly be able to write code in deep learning. But these, if you're searching, and both of these have a really large community behind them. There's other ones like MXNet, which is supported by Amazon. TensorFlow is heavily supported by Google, and PyTorch was developed at Facebook. So these are the two leading packages. So to kind of talk about traditional machine vision, it did pretty well where you would capture an image and then you would extract, certain features from these images. But a lot of these features that were extracted in traditional machine vision are kind of like designed by, these vision, experts saying, and they're kind of baked into the production software. And then you also, have to kind of handcraft the decisions of what's the max contrast, what's the defect size or the threshold, and it still can do well, but it's a lot of manually tuning. And I'll give a lot of examples of code with traditional machine vision. And here's kind of like, if you really want to learn OpenCV and be able to apply all these computer vision techniques, there's so many different techniques with this huge hierarchy. I'm not going to go through everyone, but you can do some really cool stuff with classifying textures, really cool stuff with color histograms, and also with recognizing special features like SIRF and SIFT. Real quick, Brian, I'm not sure if, can everyone see my cursor? Because I'm kind of rolling over it and I don't know.
Yep.
Okay.
I can follow you.
Awesome. So I'm not going to go over all of these, but I am going to talk a little bit about the different techniques you can do, probably 3 or 4 of these in this hierarchy. So before I go into that, with deep learning, you don't have to handcraft the features. You can actually, you develop this entire neural network and then you train on that neural network. And then it basically learns how to recognize certain patterns with this neural network. And it's very, very powerful, but there's still, it's kind of like a give and take. There's pros and cons to each one. With deep learning, you do need to have some really good training data, of course. With traditional computer vision, you can still get, you can still do a lot, right out of the box. And maybe if you even want to create training data for your neural network, you could, maybe build some really nice filters in computer visions to maybe remove duplicates, or, say I really want to quickly filter out a bunch of images that all, match a certain type for training. Maybe find a whole bunch of images that have a certain logo in it. So you can still do a lot of really nice techniques. So everything that I'm teaching with the traditional computer vision, it's not really all for naught. It's not really obsolete. And we actually have some data scientists on our team that are just been doing some really incredible stuff with OpenCV for presentations. After they run the deep learning, they do a lot of post-processing to make, to kind of, smooth out a lot of the results. So here's just kind of a quick timeline where you can kind of see, in the we had like 750s BC where people were the Greeks kind of imagine, robots appearing in Greek mythology, and then the 1960s, that's when the neurophysiologists, realized that, human vision is hierarchical. And I think that's what kind of kicked off to say, like, maybe we can start to build some AI using this hierarchy of the way vision works, and build some AI with computer vision. And it didn't really go that well from the 1970s to 1990s. It started to pick up more from the 1990s to 2012, but a lot of the techniques weren't really as successful. And then once 2012 hit with deep learning, it really just took off from there. So here's an example. So everything prior to 2012 is traditional computer vision, which I'll talk about in the beginning of this talk. And you can see this ImageNet competition was where you were trying to recognize 1,000 different categories. Is this a bird? Is this a plane? And that had, a top 5 error rate, meaning, how often when you guess the top 5 categories, how often is that category in one of the top 5? The error rate was really high. I mean, you're still guessing 1 out of 1,000, so it's still, impressive to be able to train a computer to be able to do that and read an image. But still, 28% top 5 error rate for traditional computer vision is, not, it's okay, but it's not great. But, that's, and it kind of moved like that. You would gain a few percentage points each year from 28% to 25%. And then all of a sudden, when they developed this deep learning approach, AlexNet, that's when neural networks really just exploded. They couldn't believe it went from 25% to 16% in just 1 year. And that was a neural network approach. And neural networks were designed in the 1980s, and they never really thought machine learning was kind of the state of the art then. They never thought that deep learning with neural networks could achieve such a high accuracy. And then ever since 2012, NVIDIA has become one of the most successful companies building GPUs to run this deep learning. And I mean, look what happened from 2012 to 2015. It dropped from 16% all the way down to 3.5%. And I'm not sure what the best error rate is for this competition right now as of today, but it's probably 1 or 2%. So it's been incredible what's been happening in the last 10 years. Actually, I'll pause for a second. Are there any questions so far, Brian?
Nope, nothing so far. A lot of activity in the chat, but no Q&A yet.
Awesome. So I'm going to just quickly go. I know that deep learning is kind of the really exciting field that everyone wants to know more about. But in the very beginning, I'm just going to talk about applying these traditional techniques. So there's basically like 2 branches of these traditional techniques that I'm going to go over today, which is image filtering. And with that, I'm going to show an example of noise reduction, and then also another example with classifying textures. And then there's another example of feature descriptors. And what a feature descriptor is really just a way to, take an image and be able to describe that image so you can run machine learning on it. So whether you're finding, certain key points in the image, but you're basically converting that image into numerical data. And once it is in numerical data, you can then run another algorithm on top of it. So these are just all these methods here: SIFT, SIRF, brief, orb, hog, and Haar. They're just really fancy ways to just describe an image better, to be able to do all these tasks, which I'm going to give examples of. Visual similarity, image search, classification, object detection. So here's just a quick example of denoising. This is really simple. Don't worry about the equations too much, but if you apply a filter, and all a filter really is you're, applying this equation, you're kind of scrolling left and right, applying this equation with like different patches on the image. So right here, you're applying Gaussian noise. Right here, you're applying Poisson noise, speckle noise. And you can see how, it's kind of messing up the image, applying all this different type of noise. And, with images, as you're transmitting images, or recording video, maybe even taking photography, you always kind of have that problem. Maybe there's some interference somewhere where the pictures or the video isn't transmitted, perfectly. And, you can actually very quickly, with OpenCV, be able to quickly remove this noise with a really simple equation. You just take a mean or a median filter, and it can do really well. You just apply, these filters against a noisy image. And you can see here's the noise histogram for a Gaussian. Here's a noise histogram for Poisson. Noise histogram for Poisson, noise histogram for impulse. The Gaussian formula is a little bit more complicated. So when you apply the mean or the median filter, it doesn't really do as well. But look at this histogram here where it's kind of a high and a low. And even for the Poisson, you can see how nicely the mean and median filter clean that up. And I'll quickly just show the code to be able to do this. So right here, this is the denoising. And if you want to be able to quickly run code, it can take a while to install all these packages, get it up and running. So I personally really love Colab, which is released by Google. And it's really handy because, especially if you want to test out deep learning code, which we haven't done yet, but you really need a GPU. And that can be a pain to be able to build your own machine. So you can just really quickly just change your runtime to run with a GPU. So it's really handy, Colab. And also it can be difficult to be like kind of a sysadmin where you have to install all these packages and you get all these errors. So almost everything here just comes, running, right out of the box, and you just fire it up and you run it. So right here, this is all the code, and right here this is all the code for one of the books that I originally said a lot of the code was adapted from. So you can just check out, the image processing cookbook code, and that gives me access to the images that came with that GitHub. And then right here is basically what I'm doing is I'm applying random noise here. I'm applying the random noise with the Poisson. And each time I apply noise, I'll plot the images. And in the plot images function, I have the mean and median filter, and I apply it. So then when I run everything, you can see how that's the exact image that I posted on the PowerPoint. And here's the histograms, and it's all plotted there for you. So next, any questions on denoising at all?
Yeah, there is a question. Vanessa has a question. Can you explain more on the noise histograms? What does it mean and how to understand that?
Yeah, so the noise histogram is this is how this is basically how like the values of the intensity that's being applied. So as I'm applying different noise to it, it's basically a histogram of how much those pixels are altered. So if I look at this Gaussian histogram, you can see that a lot of the pixels are kind of altered more towards this value where it's not altered as much. And then as you go further away, there's more altering of the pixels. The very high and low values, or the 0.4 and 0.4 means that these pixels are altered a lot. But the histogram just says, how often does that happen? So all the histogram really is a probability. So it's saying the probability of adding that noise at these, very high levels and low levels, it's a lower probability.
And Matt, John, there's another question. Well, there's a few more questions that we go through them. John Austin asks, what exactly is considered noise in terms of image data?
What exactly is incident noise during image data?
What is considered noise in image data, right?
Yeah, I mean, I think, that's kind of a hard question because noise is really anything that kind of causes the image to not be transmitted perfectly. I mean, with sound, you can kind of imagine imagine if I had my cell phone really close to me right now, that's going to cause some interference and some signals. And maybe if that signal interferes with this video, that's going to cause some noise, and you're not going to see a perfect picture of me. So it's something that kind of interferes with transmitting the true signal, just as this photo is the true signal of the way the photo is supposed to look like. So there's some noise in the background. You're not going to get the actual pure signal of that photo.
Mm-hmm. Gotcha.
So for classifying, I'm going to move on to, this is a little bit more complicated, for classifying textures. So don't worry about this equation as much, but basically what this is you kind of have this way to create these things called Gabor filters. And you'll see how useful this is, because if you look at this equation, you're like, this is crazy. What the heck is going on here? But what you have is basically you have this sine signal, and then you modulate that sine signal by a Gaussian, and then you have this equation here. And what's really interesting is when you apply this equation and you change certain values. So if I change the lambda in this equation, you can see how the actual width of this filter is changing. And then if I change the theta value, you can see how the orientation is changing. And right here, I'm changing the gamma, and you can see how that's making it kind of changing the height. And then the sigma actually, it doesn't just change the width, but it kind of changes the purity. So you have certain stripes. So you can keep basically like varying all these different values, and you can get, Gabor filters that kind of look like this. And what happens is when you actually apply those filters to these original images, you can kind of see how it has a different effect when I apply this filter. So imagine I take this filter and it's going, from left to right, and it's, creating all these different effects. So when I apply this filter against this image is going to look like that. So it's a big difference. However, what ends up happening is you can actually classify textures really well this way. So when I apply, let's say, these 4 filters on this original image, I get these 4 results. And then I have, let's say I take this image and I apply it the same way. I try to actually match it and try to see how closely it matches to my reference image. So this kind of looks like, some AI, some machine learning with some training data, but it's not really that. What it's really doing is I'm applying filters to an original image that is wood, and then I apply filters to an original image that's stones, to bricks, to checks, and then I just feed it a random image, of one of those 4 types, and I say which of the results most closely match the results for my reference image. And I'll quickly show the code for that. Oh, they disconnected me. That's the one part about Colab that's annoying, is you get disconnected pretty often if you're in the middle of running something. But so right here, I have the Gabor kernels, but see, I have these images right here, the image names. So I have those 4 images, and then I run the kernels, this Gabor kernel right there, on these 4 reference images. And then what I also have, if we go lower, is these are the new image names. So since I already ran it on the reference images, and then I run it on these new images, I can then match it and say which of these new images, are the closest match to the results of what I got with the Gabor kernels. And you can see, here's the code, working right here. And all these things, yes, it is a pretty complicated equation, but you don't really need to like derive that equation from scratch to be able to do this. A lot of these things, that's what's so handy about OpenCV is, a lot of these things are there. And also it's not just OpenCV. Here's another really great package, SK image, and that imports the Gabor kernel. So that's just a quick code example. I want to try, do we have a hard stop at 6:30 for questions, Brian?
This is Tommy. Yeah, I mean, we can go, go with the flow if you still continue to go.
Okay.
That's on you, because you're answering questions as we go, so it should be fine.
Okay. Yeah, I want to try to, because I don't want to spend too much time on the traditional computer vision, but I'll try to, if there's some questions, interrupt me. But here's another really cool technique called the histogram of gradients. So what you're basically doing with this is, let's say you have, this photo right here of, I think that's Manu Ginobili. So you take that photo, and let's say you want to try to, define the areas that are, really, prominent. And you can actually calculate the gradient, the difference between this pixel and that pixel. But it's a little bit too slow to be able to calculate the gradient for every picture. And to kind of talk about the gradient, all a gradient really is just kind of calculating the difference, saying like, it's almost like take every pixel in this image and just put an arrow, to replace every pixel with an arrow, and that arrow has a direction, and that arrow also has a magnitude. And that's really what the gradient is. And that's really difficult to compute that for every pixel, to say, is the intensity increasing in that direction or in that direction? And how much is the intensity increasing? So what you can do is you take this filter right here called a Sobel operator. And when you apply it, it basically gets rid of a lot of the parts of the image that are not important, and just makes the areas that are really prominent, it retains those. So it kind of simplifies the image to make this operation less expensive. And then you can run the gradient and compute it from there. So when we do this on the whole image, and then we run this operator, you can see how this is, how the gradients look on this image, which is really cool. But the problem is we want to be able to represent this image in a way that we can, build some AI to be able to classify it in some way. Like, is this a runner, or is this, a swimmer? And if you just calculate these gradients, it's not really useful. When you're doing machine learning or AI, the main trick is just try to get my data to look like Excel. Just try to like have every image be one row with a whole bunch of numeric data. And by running this gradient, you can't, that doesn't really help you as much. But what you can do is let's say you divide this picture into, 100 by 100 cells, and then you calculate the gradient for each of those cells. And what ends up happening is you have the magnitude and you have the direction for the gradient in each cell, and then you create a histogram. So right here, the direction is 10, and the magnitude is 2. 10 is just an angle for this, cell. So you just divide that, because you have 0 and 20, and that's 10. So you put 2 twice there. But for right here, the direction is 80, so you only put it once there. So that creates, a really nice histogram. Move this. And that is a histogram that basically, completely describes the image. And what's really useful about this is, now that you have this histogram of gradients, you can then do a standard, machine learning technique to be able to classify the images. This is something, logistic regression. I'm pretty sure Jing probably covered that last week, but don't really worry about the equations too much. But this is basically like a yes/no classifier, or you can do it in a way that it can classify multiple classes, doing this thing called a softmax regression. So when you run that against the histogram of gradients, it's really cool. You can actually, recognize all these different images. To quickly show the code for that, here's just an example. And these are all notebooks I can share after the class. So right here, this is just an example of running the histogram of gradients for this image. And as we go down, this is actually where I downloaded a whole bunch of photos. Really nice with Colab. They have like a hard drive for you. So I downloaded 101 photos from this of flowers. And as we go down, here's all, or sorry, this wasn't flowers. This is 101 categories from Caltech. So I filter out all them. So I basically reduce it from 101 to 10 categories. And then as I run this, these are all the histograms. And then you just run that through a classifier. And you can see here's all the different classes that were recognized. So it does pretty well. It doesn't do as well as deep learning. However, let me see. Yeah, so right here it says like, this is a pigeon, but it recognizes it as a brain. But it still gets, pretty good accuracy. I think we were 83% accurate, so not that bad. Now let me go back. Any other questions so far?
Yeah, there's a few. Brian, you got those?
Yeah, let me pull them up right now. So one of the questions is, and this is from some of the content later, but does it compare the random image to all the Gabor filters to determine the texture of the random image?
So you basically, what you're doing is you take a image, and you run, so many Gabor kernels against it. And the results of that, you compare that to all the results of the reference images. You won't have that many reference images because you only have one reference image per class. So if you're only trying to recognize 4 patterns, and let's say you have, different Gabor kernels for each reference pattern image, you compare the results from the image you're testing with the results from the reference images. So you're just basically applying Gabor kernels for the reference images, and then Gabor kernels for the test images, and you compare those to see which are the closest match.
Gotcha. Nice, thanks, Matt. And one other question. This is from content that was further back that I apologize I didn't get answered, but it was back when you were talking about filters and Gaussian filters. So Deb Vorndran asked, she had questions around how to apply those type of filters to thousands of images at a time. The concern being that, it appears that a human has to look at each filter and pick the best one, and she doesn't understand how the filters can be done, at scale.
Yeah, it's that. I mean, that's sorry, I keep getting these surveys. That's tough. Scaling. I don't know if I have a good answer for that. I think probably my good answer for that is it's easier to scale with deep learning. I mean, you can apply the mean and the median filter and see which one does better, cleaning up the noise, but you do kind of have to eyeball it. I mean, there's more advanced ways to see where you can kind of compare maybe I mean, there's probably ways you could do it without deep learning where you basically apply the mean and the median filter, and then you look at the image that was cleaned up and you compare that to the original image, and you look at all the different filters you tried and tried to see which one was able to retain the originality of the images the best. You might need some distance metric between the original image and the cleaned up image, and then you just take like an average of that distance metric from original to the noise the noise reduced image.
Mm-hmm. Yeah, I'd agree with that, absolutely. So there's another question on, let me read it real quick. Do we use deep learning with HOG? I assume HOG, I assume that's histogram of oriented gradients. I don't know if I said that correctly. Yeah, that's the question.
So with HOG, the example I just showed is no deep learning. So there has to be a neural network for there to be deep learning. However, you could HOG basically creates a numerical, a numerical representation of an image. So that you could, and I'm showing an example of using machine learning with a multinomial, using a classifier with machine learning to be able to train it and predict the right class. However, there are approaches that are coming out with deep learning to be able to read structural data. And you could, there's nothing stopping you from running a neural network onto the data that is created with Haar. However, I'm not sure if I'm answering the question correctly, but if the question is do you use deep learning to create those representations with Haar? No, you don't. So the representation of the image that was created with Haar, there's no neural networks and there's no deep learning with that.
Mm-hmm. And then on that same topic, Ryan Walden asks, are you able to obtain a lower dimensional representation of the image using this method?
Well, you know, I mean, it is kind of a lower dimensional representation because it's a distribution of each angle. So, you know, the image is like 10,000 by 10,000 pixels. That's a huge amount of dimensions. So, you know, if you use Haar and you only have like 10 dimensions of each angle, just depending on how granular you're going to be, it's going to be a huge dimension reduction. But, you know, there's a lot of dimension reduction, you know, methods that you could do beforehand as well. But, you know, I wouldn't, you know, Haar is just kind of a way to kind of convert an image to you know, to just kind of say, this is how the gradients look like with this image. So kind of yes, kind of no, I guess is the answer.
Great. Yeah. There's some hard-hitting questions. I wish I could have answered those ones in the chat, but I had to pass them over to you.
Yeah.
Great. Yeah, that's all we have so far right now.
Okay, cool. So this is something I want to try to have enough time to do the deep learning. So I might kind of do this part a little bit faster because it seems like if we go into the details of all these different descriptors, we might not have any time left for the deep learning. But what these feature descriptors are basically, you're trying to find these key points in the image. And these are really useful. Like, let's say, you know, you're trying to filter out saying, I want all the images on my iPhone that are of the Golden Gate Bridge. And the Golden Gate Bridge, you might have taken at a whole bunch of different angles. And, you know, how could you quickly do that? You know, with just using OpenCV to, let's say you have 1,000 images. So basically what these descriptors are is they try to find, you know, key points in the image. And one of the first key points was, let's just find a corner in the image. And, you know, if you kind of look at the before and after, you can kind of see how that's a corner. But as you zoom out, it's finding corners in different places. So corner detectors are not rotation invariant and they're not scale invariant. So the very first key point detector was this thing called SIFT, which was a scale invariant feature transform that works a lot more robustly than a corner detector. And the way it works is you're kind of, you know, taking this Gaussian and you're basically taking it with, you know, you do different scales and then you take the difference of the Gaussian. So you can kind of see how this image looks a little bit different as you know, apply more noise or less noise. And then you can actually take the difference between those Gaussians. And what ends up happening is as you're doing that, you take the difference of the Gaussians and then you also change the scales. You're going to find like certain areas that are really prominent in the image. And if you have the same areas that are prominent as the scale changes, so imagine when I, you know, take these difference of Gaussians and there's really prominent areas with this hat, and then I zoom in, I zoom out, I make the image smaller, and the key points always stay the same, then you know that's a really good key point to keep. And here's just an example of what ends up happening. So when I look at this image right here, SIFT is finding all these different key points. Then the next technique was this thing called SURF, which is essentially the same thing as SIFT, but what it does is instead of it's basically trying to find prominent areas in the image again, but it tries to do it in a faster way using a box filter. So this is still the if you want to do some reading on the side, you can read about how if you take a Laplacian of a Gaussian to an image, it's really cool. What it takes, like these two second order derivatives. It's super robust, and it will find all the prominent areas of the image perfectly, but it's so slow and it would just take forever. So what you're basically doing is you're using this thing called where you take different levels of noise and use a difference of Gaussians, so you don't have to do a full Laplacian. So it's kind of an approximation. And SIRF is the same thing, of where you're doing that approximation, but you're using a box filter, and it's about 3 times faster than SIFT. And it's really good at handling blurring and rotation, but it's not that good for, for the viewpoints changing or the illumination changing. So you're sacrificing a little bit, but it is 3 times faster. Here's an example of SIRF. You can see how it finds these key points for the butterfly really well with all these different blobs. And here's an example of, like, let's say I want all the photos of this temple. This is an example of how you can do image similarity with SIFT. And even if you rotate it, you can see how the key points, keep matching each other. And here's a really poor match with only 2 matches. And here is a very poor match with 4 matches. But it does pretty well, if we want to, find all the photos of this temple, look at, all the top results, that no matter how you modify this image, this has 114 matches, 76 matches if you crop it off. So this can be pretty handy, and this is no deep learning at all. I do have code examples for all these, but I'm not going to show them, just because I want to get to the deep learning. And I know we have a hard stop at 7, and I want at least to have a half hour for the deep learning. But I will kind of just show a little bit more examples. So the problem is with SIFT and SIRF is they still are kind of slow. And actually, in my code examples to run these, I needed to install OpenCV like 3.3, and the latest version is 4.2. And the reason for that is because OpenCV is SIFT and SIRF. These approaches are patented. So if you actually install OpenCV 4.2, you couldn't even use these approaches. You would have to, purchase a license for SIFT and SIRF, which is, kind of annoying. But then again, you can just install an earlier version of OpenCV of 3.4. But if you memorized all the commands with 4.2 and that's what you learned, there could be some differences. If you're doing, simple stuff like draw a rectangle, it might be like a different API command. However, the flip side of that is other approaches have been developed in the last 10 years that are actually, work even better than SIFT and SIRF, that are even faster. So I'm not going to go too much into the details of these, but this is FAST that finds key point detectors, and it's super fast. It actually does this in a circular method. Where you find a point, you look at the radius, and you're trying to figure out, how often the 16 points around that radius are of a different intensity. And it does a kind of iterative way where it starts with 4 points, and if those 4 points don't change the intensity that much, then it goes to 16. This is, so the question is why am I showing both of these together? And the reason for that is fast and brief are totally different. This is a key point detector, but we were doing similarity back here. So even if you find the key point detectors, how do you find the similarity between those points? And to find the similarity is pretty slow as well for SIFT and SIRF, because when it represents those key points, they're represented from 64 to 128-bit floating point numbers, which is crazy. So brief is just this really advanced way to represent key points with a binary representation, so it's super fast. So it's kind of that step, you know, you use fast to find a key point, and then you use brief to represent that key point. So you can quickly, you know, run image similarity really quickly. The way it works, you know, really quick, you have a patch, and then you basically are kind of like creating ones and zeros as you're kind of going around this geometry of that patch. You know, is this patch, does this, you kind of keep taking pairs of pixels within this patch, within this key point, and you say, you know, does this pixel have less intensity or more intensity than this other pixel? And it creates a whole string of ones and zeros. So it's much better than 128-bit floating point numbers. So, and here's just an example, you know, of all the different intensity, of all the different, this is actually the recognition rate when you convert that key point. And you can see how well it does with all these different geometries of creating these binary representations of these key points. So what ends up happening is you can see how well it recognizes this face, and then you twist that face. It does a really good job of recognizing all these key points when you do fast and then you do brief. So I want to kind of get to the deep learning. I think we're almost around to 6:30. So this is orb. So what orb is it does fast and it does brief, but the problem with brief is that, yes, it is a great binary representation of these key points, but if you rotate images like we did in this, a lot of the information gets lost between the key points found in this rotated image and the flat image. So orb is kind of like this, where you're using fast, but you're doing some manipulations to make it more robust to rotating. And here's just the equations of how it basically learns the orientation of the key points. And then when you run it against another image, you try to correct the orientations. And you can see how a lot more key points were found. I think it is in the code. In the notebook that I created, it says how many key points were found. I believe 42 key points were found with fast and brief. And then when you use orb, you have 98 key points that were found. So if you're trying to do, you know, visual similarity or filter out images of a Golden Gate Bridge, this is the way to go, you know, to use orb. And also, you know, here's another example of a NASA image. And this just kind of does this ratio test to say, you know, where were the best key points found? And if it finds them all in the same area, it can remove a lot of the other key points. So it basically, all the ratio tests is it kind of cleans up the key points that were found in the wrong area. So it kind of is a good way to figure out, you know, where's this NASA logo in this building. One other thing is for object detection, just like what you did with this NASA. This is another really cool thing where you create different features. These are called Haar cascade features. You've probably seen this a lot, but these are all kind of handcrafted, but it can still do pretty well where you kind of create these blocks saying, like, you know, maybe this is the way a nose is shaped, where it goes, you know, low intensity, high intensity, low intensity. This is maybe the way, like, to recognize a rectangle, where there's, you know, low intensity and high intensity. But, you know, these features get a lot more complicated. And what you can do is, you know, a lot of people have handcrafted features to recognize certain points. So when you run those handcrafted features against images, you can then, you know, let's say you have a handcrafted feature for a face, you can recognize, you know, faces pretty well. Or you run one of these handcrafted features for an eye, and then you recognize an eye pretty well. And it doesn't do perfect. You can see how Charlie Chaplin was missed here. Mother Teresa, her nose wasn't recognized. But you know, that's so these are all, you know, standard techniques that can get you up and running out of the box pretty quickly with computer vision. So before I start with deep learning. Any questions on the computer vision part?
Yeah, so there's a few questions. David Torres asked, do color images change the dynamic of any of these methods?
Yeah, they can. In the code that I'll share, especially if you're trying to, recognize between different intensities, it can do better by converting that color image to black and white first. And I do that in most of the notebooks that I'm sharing for these techniques.
Gotcha. And other questions related to your work at Home Depot. Madi asks, how regularly do you use these traditional methods in Home Depot to compare to deep learning methods?
Probably 10% of the time. I'd say we probably should use it more. I'd say we have certain advantages because we can start, certain jobs where contributors will answer questions. If we want to create, a training set saying, give us a whole bunch of product images that are forward-facing chairs with a nice white background, we could spin up a really quick job, with getting contributors to be able to answer those questions, multiple choice online. But I'd say we should probably use it more because it would help, filter out a lot of images to create training data. And we do use it also to clean up a lot of the results.
Yeah, that's what I was thinking. Great. And there's one more question. Ismail asked, he says he's seen Haar features in large XML files. Could you explain how those files are generated?
That's a good question. If I show the code, if I have some time at the end, I'll show the code for Haar, but I'll also share it after this talk. But I'm not exactly sure of the XML format, but basically it is an XML format that explains how these features are created, where the blocks are. So it would be cool if we could find a tool where it converts that XML into the feature that looks like that. I've never created a Haar feature myself, so I'm not exactly sure how the format is, but they do provide those XML features with iXML and Haar feature for recognizing noses, Haar feature for recognizing mouth features, mouth features, and then you just read it into OpenCV and then you apply that filter around and it recognizes everything.
Mm-hmm. Great, thank you.
Sure. So we have about a half hour left. So for deep learning, this is kind of like a really exciting field because as I was kind of talking about before, it's just been incredible, all the different results that we've been able to achieve. It was like to be able to recognize handwriting, if you ever use like a watch and you're doing scribble or recognizing a voice, if you kind of remember how poorly 15 years ago, if you ever, called customer support and was trying to recognize what you were saying, you always kind of dreaded if it was one of those automated responses based on your voice because it always worked terribly. And actually, when the iPhone first came out and it had the voice to text feature, I was so traumatized by how poorly all those algorithms worked. I just wouldn't use it. Everyone told me it worked really well, but I was like, I'm not going to bother. But deep learning with recognizing images, with recognizing sounds, it's been incredible, the leaps and bounds that we've been able to make. A lot of the reason for that is not just the algorithms, because neural networks have been around a long time, but it's also because the hardware has just gotten so much better. Neural networks were pretty much ignored, until 2012. And then NVIDIA kept coming out with more and more powerful GPUs and AMD as well. I don't want to be too brand loyal, but it just became so powerful. And then they just decided to give it a try again. The neural networks came out in the 80s and they decided to give it a try during the ImageNet competition, and then the results were through the roof. But there was also a few changes to the neural networks as well that was able to get really high accuracy. So I'm going to talk a little bit about classification. I'll talk a little bit about object detection, and I'll talk a little bit about segmentation. So classification is basically where you just want to recognize the type of the image. And object detection is where you're trying to locate in the image the actual, objects in the image, whether it be finding the dog, finding the horse, finding the person. So it's a very different task than classification. And segmentation is an even more advanced task where you're not just trying to locate it with a box, but you're actually trying to locate all the pixels, exactly the pixels, and do a really nice tight outline and be able to segment that image perfectly. All these tasks worked pretty terribly. Well, terribly in the sense, if you want to achieve higher than 80% accuracy, they didn't really work that well without deep learning. So let's talk about this thing. So even neural networks didn't really work that well either. And what ended up happening was in 2012, there was this competition, and they just came up with this approach called a convolutional neural network, which is very different than a standard neural network. And that is right here. That is AlexNet right here in 2012, where you get the big jump. So just to show an example of AlexNet. So you have the input data in here, and then you do these things. The comms are convolutions, and then the FCs right here are fully connected. So I'll talk about what all of those are, but you can see these are all the operations for AlexNet, where you do a convolution, and there's all these things that, there is going to be a workshop at Southern Data Science Conference where I'll be doing an 8-hour talk. So I can talk more about, all these different operations during that talk, because it's super hard to do this all in an hour. And I have a feeling I might go a little over. But so the convolutions, but I will talk about these things right here. The filters and stride, those are specific things, but you have a convolution, you have a max pooling, and then the FCs are fully connected. So what do all these things mean? I mean, a lot of people might have used these neural networks, but they might not, be totally familiar with what these things are doing. So if we kind of look at this neural network, look at the layers of the neural network from the very early parts to the very later parts. What are these layers learning when we're doing those convolutions? So a convolution, all it really is you're coming up with weights. You're trying to learn weights to multiply against little patches of this image. But what do those weights look like? So you can see in the earlier layers, these weights are basically, just looking for different types of edges. But as the later layers, you can see how these features become a lot more dense, a lot more rich, much more higher level features. You can see how much more detailed and complex the weights that are being learned at the later layers. So let's talk a little bit about what each of these operations are doing. So a fully connected network is, let's say you have all these layers of values. So you can see in AlexNet, the very last layer is fully connected. So you're feeding that into a fully connected layer, but by fully connected, it means that all of these weights are being applied to each area in this layer. And when you do that, it can work really well. It's very complex, tons of weights, tons of multiplications, and it can, it makes sense to do that at the very end, because you're basically taking all the features that you learned and you apply a fully connected network to basically convert that into a probability. And that probability is right here. This is a 10 by 1. So this means the probability of each of these classes that's trying to recognize. So for the ImageNet competition, which I've been talking about for a while, that is trying to recognize 1,000 classes. So in that case, you would have 1,000 by 372 weights, and then you would have a probability for each of those classes, and then you pick the class that has the highest probability. So a convolution, what that basically is doing is you don't have as many weights to learn. It's not fully connected. There's not as many multiplications, but it's just extremely powerful because you're basically taking these 9 weights in this example, and you're trying to learn 9 weights that can actually perform really well and give the highest accuracy possible. And you're multiplying these 9 weights across the whole image. So in this layer, this would be a 5 by 5. So let's say you have an image that's 32 by 33, 32 by 32 by 3 image, and you have a convolutional filter. You would be trying to learn the 5 by 5 by 3 weights that are most appropriate, that are going to give you the highest accuracy. And then when you convolve it, it's making it smaller. So that's what's happening here. If we look here, you can see how as we're doing these convolutions and neural networks based on the size of your convolution, the whole layer gets smaller and smaller from the result of this multiplication with the convolutional multiplication. And that was really the groundbreaking thing. And also what was groundbreaking is between each of these layers, if you're just adding and multiplying, it still is a very linear operation. So you have, certain activation functions that are between these layers, whether that be a sigmoid for probabilities, or hyperbolic tangent, or a ReLU where it just chops off the negative values, but it adds a lot of nonlinearity to this network. And with that nonlinearity, it makes it even more powerful to be able to recognize this. And that's why you're getting such high, you have so much higher accuracy, because it's a large network, and it's got a lot of weights it's learning, and it's got nonlinearity, so it's very complex, but the NVIDIA GPUs can handle it, and then you're getting huge jumps in accuracy due to the complexity of these convolutional neural networks. And that's just AUXNet. I mean, these networks can get huge. So pooling, that we saw in AUXNet as well. So pooling is not really the same as convolution, but you kind of rotate it the same way. Max pooling is very popular. So as you're kind of, rotating around this image, you can see how this box gets also converted into a smaller box when you're doing pooling. But for a max pool, you just take the maximum here. So you can kind of see in this area right here, the maximum is 3. And then as you kind of scroll one over, the maximum of those pixels is 2. And that's all a max pooling is. They also have average pooling, but max pooling is a little bit more popular. So those are really the operations in AUXNet. And that's why with all those advanced operations and learning, all these weights, you get, really high accuracy jumps from let me just, from 25% to 16%. So, but these networks get even more complex. AUXNet, yes, it goes down to 16%. Yes, it's awesome. But, from year to year, they kept coming up with even more complex networks. This is another network which I have in my example code, VGG16. This is, you can see how many more layers there are, much more convolutions. They get a little bit smarter by they add more layers, but each convolution is a little bit smaller, a 3 by 3. I think they got rid of all the 7 by 7s convolutions. And it just kind of created this network that was able to, make it even more accuracy. You can see how they have convolutions, then pooling, then the fully connected networks. and it does that whole process. And I believe this is VGG16. So if we go back to that graph, yeah, so right here, 2014, that came out 2 years after AlexNet, and that was at 7.3% error rate, so much lower than AlexNet with all that complexity. And the one thing I also want to show is, here's just kind of an overview of all these networks. And this came out, you know, 3 or 4 years ago. So this graph is a little bit older, but one of the state-of-the-art networks at the time was ResNet and Inception. And you can see what's basically going on here is, look at the computational cost of VGG. Yes, you got, you know, 75% accuracy, but they came up with all these different approaches of ways to do convolutions, and to make it even more accurate at lower cost. So it has less number of operations, less number of parameters to find. So Inception v4 and ResNet, I think Inception v4 was the highest accuracy at the time, but look how much lower computational cost it has compared to VGG. So it's, I mean, that can be kind of rewarding in a way as you're, learning some architecture and trying to design a new neural network, and you're like, wow, I even got more accurate and less computational speed. So with that, before I move to object detection, any questions on convolutional neural networks?
Nope, nothing. You're over my head now. Might be over everyone's. No,
Yeah.
questions now.
Yeah, do we have a hard stop at 7? Because I wonder if I'm going too fast, or I can maybe just do a quick overview of object detection and segmentation.
Yeah, I would say let's do a quick overview of object detection, and then we'll kind of stop around 7 for any questions that the audience may have, and we'll make sure that we share out all the content that we may or may not have got to.
Okay, perfect. Really quickly, I'm just going to show some code for the image classification. So this is pretty cool. So this is where TensorFlow and PyTorch come in handy, where you can just do a quick checkout, and then you can see right here, this is PyTorch, where I say, give me this model, which is VGG16, and then I classify it. And when I do this classification, I feed this image, which is a cheetah, and I say, top 5 classes that were predicted. It says almost 100% that this is a cheetah. Really easy to do this, pre-trained model, VGG16, PyTorch, classify, boom. Here's another one that, but this one doesn't work well because this is an octopus. However, that's not one of the 1,000 classes that were pre-trained in ImageNet. So pre-trained, it has to be pre-trained on some data. It's pre-trained on ImageNet, where it tries to recognize 1,000 classes. But if octopus or anything else you're trying to recognize isn't in one of those classes, you're really out of luck there. So what you can do is you can do this thing called fine tuning. And here is just where I'm saying, I just want to build a classifier for recognizing flowers. And I'm downloading all these flower photos, and I'm going to quickly go down in the code. And when I run the classifier, you can see how it recognizes daisy, but it says this is a vase, this is a bee. These aren't, flowers that it's recognizing because I'm using the pre-trained version. So if I, take in VGG, the same thing, and I say include top equals false, meaning I'm going to chop off the last layer. That last layer is going to tell me what the class is. But to me, that's worthless to me, because I don't care to use it, because it's telling me the class of one of those 1,000, and I want to know flowers, and flowers are not in one of those 1,000. So I'm going to just chop off that last classification layer. And then at the very bottom here, what I can do is now I have that model with so this model right here has the layer that is chopped off, and I add another layer, and I say, instead of trying to recognize 1,000 classes, I only have 5 different flowers I'm going to try to recognize. So I'm adding a classification layer of 5 different classes. And this is the network. And then basically I just run this on the data. So when I have this train generator, that reads the folders that I created. So I have basically, I don't have enough time to show the directory structure, but it's basically train, 5 flower classes, and then all the images for daisies in one directory, all the images for violet roses in one directory. And so it automatically knows what the right class is by the directory structure when I'm training it. And this will give me an error if I put the last layer as, instead of putting a 5 there, if I put a 10 there, it'll say, you know, it'll say, what the heck? Like, I see 5 directories and your last layer has 10 classes I'm trying to recognize. So it's really nice how it checks for that. So I run this, you know, a class. I run this network. It goes for around 20 epochs. Then I can save it after it's done training. And then here's the training and validation accuracy. And then I take that same model that was fine-tuned, and I can predict on it, and you can see how these are all flowers right here. So really cool how you can do that with convolutional neural networks. You can choose different networks. If you don't want to use VGG16, you can use other ones. So here is what object detection is. I have 2 other notebooks right here. So I know we're running out of time, and I won't explain object detection, but what this notebook right here is, it's a real quick way to recognize images. And these are pre-trained as well, but this will actually create the bounding boxes. I think I actually didn't run this before. So when I share this notebook, I'll have it run already so you can see what it looks like. But I have the screenshots in the slides. And actually, I also have another notebook with segmentation, but this is basically what object detection is, where we have, you know, different squares and we're trying to recognize the right classes. And object detection wasn't really that popular, and then it really started taking off, as you can see from 2012, the number of publications. And the main thing to know with object detection, is I know I'm running out of time, is there's 2 different types. There's 1 stage and 2 stage. And what happens is you have 2 stage, and what a 2 stage object detection is it tries to have a model that kind of learns where the candidate boxes should be. And then it takes those candidate boxes and tries to adjust them and have the right coordinates, you know, resize them. But you have one model for saying, here's a whole bunch of candidate boxes where objects may be in your image, and then another model to predict the class and predict the actual, and predict the resizing of that box. A 1 stage says, you know what, I'm not going to create any model to learn what these candidate boxes are. I'm just going to give you every box that could be possible. And it runs faster, but it's not quite as accurate. But for a lot of people who love object detection for, you know, using iPhones and mobile, so these 1 stage models are getting more and more popular. But here's just kind of, I'm going to skip this, but this, I'll share it, but this is just how we evaluate object detection, which is just, you know, basically precision, where you do intersection over the union, and then you run the precision to see how often you predict the right class. And here's just, you can see how all these models are kind of changing in accuracy. Here's a SSD, which is the one that I had in the example notebook. And you can see how, you know, how the accuracy keeps jumping as we get, you know, more and more mature with all these different data sets. And don't worry about this, but this is just saying that these models also can vary based on what network you choose. So as I showed VGG16, you can choose to use SSD with VGG16, or you could choose to use SSD with Inception or SSD with MobileNet. So it's kind of that it's kind of that give and take where you're choosing the network to use, and then you're choosing the object detection approach to use. So I don't know if there's enough time to explain how the SSD works, but
I would say, Matt, if people want to stay on,
Okay.
you could definitely go over. Right.
Okay.
Thank you.
I want to apologize for everyone that had a hard stop at 7. I probably spent a little bit too much time on computer vision, but this talk also is being recorded. So if you do have to leave at 7, definitely feel free to go ahead and download it. And I'm also going to share the notebooks shortly tomorrow, and also I'll share the slides as well. So I'll talk a little bit about how the SSD works. So you can kind of see how you don't have a network to decide the candidate boxes. So it basically says, I'm going to give every single possible box for every single grid. And these grids, change based on the layer that you are extracting from. So it gets really crazy. So so this right here, you can see how this is the network that I just talked about, which is VGG16, the same convolutional neural network. So what ends up happening is I just basically am running a convolutional neural network, and then I'm trying to extract from those layers all the information I'm getting to be able to learn, figure out what's going on in this image. So it's really cool. You're running this convolutional neural network, and then I'm trying to extract information from each layer. So it's pretty nuts what's actually happening. So there's a total for each of these layers. I have convolution number 7. I can make, that is a 19 by 19 layer. So I can make right there 2166 boxes, because I have 6 boxes per each little cell here. And for, let's say, convolution number 8, when I'm extracting information from there, since it's a little bit smaller, there's gonna be less boxes. But you add these all together, you're getting, no matter what, every time you run an SSD, you don't have a network to propose where the candidate boxes are, but every time you run this thing, you're gonna get over 8,700 boxes, which is pretty nuts. And what ends up happening is the boxes are different sizes, based on, whether you're doing an 8x8 or 4x4. And the advantage of that is if I have this 8x8 feature map, depending on what layer I extract from, each layer has, different sizes. So the 8x8 feature map is going to do really well for recognizing smaller objects, like this cat. And then for the dog, that right there, I would need the 4x4 feature map. So that's the advantage of extracting from different layers, is you have different sizes, and it can really work to your advantage based on what size of the object you're trying to recognize. The minus of this SSD, though, is look at the very first layer. So you can see 8x8 work pretty good for recognizing this cat. If you take the very first layer that the object detection is learning from, it's 38 by 38. So that's still a pretty big, reduction from the original image. So SSD isn't going to do that great in recognizing very small objects. Like if you were trying to recognize, we kind of have this when we're trying to recognize vases and living rooms, and it's kind of deep in the background. SSD would miss them. But if you're trying to recognize chairs, which take up 20% of the image, SSD should work great. It just depends on what types of objects you're trying to recognize. For furniture, it's going to work awesome. Just another example of how the different size of the layers causes different size of the objects to be able to be recognized. I'm not going to talk about this. This is just all the math involved with SSD, but basically you're penalizing when you're wrong. That's what the loss function is. So you're penalizing when you predict the wrong class. So that's what this conf right here is the confidence of predicting whether it's a dog or a cat. And then the location is how tight is that box around that cat and the dog. So, all the original techniques I spoke about with traditional computer vision, you'll notice one of the advantages of, recognizing faces with Haar or recognizing that NASA logo. You don't, really need you don't really need a lot of training data. For these, they're super powerful, but it can be, really hard to get up and running. You might have to start, maybe a job with contributors or do it yourself where you're drawing lots of bounding boxes. Usually you want to have about 100 examples of each class. So to draw all those bounding boxes manually, for let's say you're trying to recognize 100 classes, that could be, easily 10,000 images, if you want to get this accuracy pretty good. So that could take a while. There's examples online of this link of recognizing just macaroni and cheese, and that's easy. It's just one class, you do 100 images and you can, train this up and running. That being said, though, if you want to be a practitioner in this, there's plenty of training sets online that you can just download where it's already done. And that's, basically what a lot of this research is doing. They're using you're using data sets that are already created to be able to test how well their model is doing. There's a lot of public data sets that are huge with object detection and with segmentation. Here's just an example of three different ones. So this faster RCNN is the two-stage approach. And you can see how it always has the highest accuracy. And SSD does pretty well, but as you get to smaller objects, SSD and YOLO are the single stage, and it just doesn't do as well as the two-stage approach with the smaller objects. Also, this is just another graph here with the GPU time and the overall accuracy, and you can kind of see how how you get more accurate as you. So faster RCNN with that's the two. So faster RCNN is a two-stage approach, and then it's using inception, which is a really complicated convolutional neural network. So you can see how that takes an extremely long time, but the accuracy is really high. If you're doing, let's say, SSD, you can see how fast it is, but you do take a pretty big hit in accuracy. 25, the precision there is 25. So any questions on object detection before I move to segmentation?
Yeah, so we do have a few questions. I'll stick with this one because it's kind of recent. Mahdi is asking, what do you mean by recognizing different chairs?
What I mean by recognizing different chairs is if you had an image, and let's say you trained an object detection algorithm to recognize chairs in the photo, SSD would work really well for that because normally chairs in the photo in living rooms take a pretty good chunk of the image. But something like vases or candle holders usually take a very tiny fraction of the image, and it wouldn't really perform as well with that.
Nice. Ismail asks, when do we decide to use deep learning instead of basic feature extraction using OpenCV and some of the other packages available?
I would say if you want to train anything for production, deep learning is going to be the way to go. Mm-hmm. There can be certain ways where OpenCV can help, where you can, or a traditional technique can help. where you use deep learning first, and then let's say the segmentation doesn't really have a very nicely thinned outline of that person, you could use OpenCV to kind of touch it up a little bit with a traditional technique. And we have done that, and it does a really good job of touching up, and it also does a really good job of filtering images to use for training. But if this is something for prime time, where you have a mobile app, and you want to recognize, I'm always saying furniture because that's what we're working on with Home Depot. You pretty much have to go with deep learning. There's really no way around it for something for production. It's going to give you the highest accuracy, and and iOS and mobile, they're really building things to support Google Cloud, or really building things to support TensorFlow and deep learning models. Not as much with the traditional techniques. The traditional techniques are really good for doing demos, to kind of give demos of images, to maybe say like, oh, here's all the forward-facing images of products with white backgrounds, and just to do some quick stuff, maybe in a notebook of code to kind of present to someone. But production code, I think you got to go with deep learning.
Yeah. Great. And I'd say, and I'd 100% agree with that as well, from what we say. But one final question here is, it's related to the kind of tool sets that you prefer, specific to your work at Home Depot. So there's questions of, which deep learning library you prefer, PyTorch or TensorFlow?
That's kind of a loaded question. I think I like PyTorch so much that I think maybe it's too much, because I think sometimes I meet other people that are using TensorFlow and I'm like, how could you, how dare you, how could you do that? That being said, TensorFlow did come out with a new version, 2.0, which I do have some sample code, which I'll share, and it's gotten a lot better. However, I just find that debugging, even with 2.0, PyTorch is just so much easier to write the code.
Mm-hmm.
The flip side of that is when you want to move things into production, it's so much easier to do it with TensorFlow. If you want to create a mobile app with Android, it's all right there to quickly do a drag and drop of a TensorFlow model, because Google did TensorFlow and Google does Android. And also Apple is really building a lot of products with Core ML to natively support TensorFlow.
Yeah.
There is a PyTorch mobile that has come out that looks pretty promising, but I don't think it's yet ready for prime time. So I usually try to do a little bit of both. I'd say if I'm trying to figure out the right deep learning model to do, and I'm testing out a lot, then I go with PyTorch. And then when I decide, that this is the best segmentation model or the best object detection model that we're going with, then I'll just go and redo it in TensorFlow.
Yeah. And also in part of this question is, do you prefer, and this is going to be based on different project, the type of project you're working on, but the question is, how do you prefer classification versus detection versus segmentation? And then the second part of it is, what type of valuation metrics do you care about, right? And I know that's also probably a loaded question that you want to answer, but it really depends on the problem.
Yeah. I think it totally depends really on your problem. A classification works great, if you're trying to, just trying to predict, let's say something like, let's say you're just trying to predict certain photos of is this a photo of a person? Is this a photo of an animal? Is this a photo of certain products, of certain furniture that you're onboarding? What type of furniture is this? Also, classification works awesome for visually similar, because it learns a lot of the features of the image so well because you're throwing that through a convolutional neural network. So you can just chop off the classification layer and then use the most recent layer, and you have all this rich information about the image. And then you can find, maybe similar looking chairs that way and use visually similar. So I'm a huge fan of classification, but there's sometimes where it just doesn't work well, even with visual search. Like, let's say you're, shopping at Home Depot and you want to find out where this screw is, or where this screwdriver is in the store. You want, and you bring that light bulb with, or a light bulb, you bring the light bulb with you and you take a picture of it. You would think like that's a classification problem, but it's actually not, because there's so much noise in the image. When you take a picture of it, maybe you took a picture of the light bulb, with your hand holding it. So you kind of need to use object detection to be able to crop out all the noise before you try to find, a similar light bulb, to be able to crop it perfectly. Maybe you even have to go to the next level and use segmentation and be able to, do a perfect outline of it. So it really, depends on the problem. Evaluation metrics, precision, recall, works perfectly for classification. For object detection and segmentation, not as much. You kind of have to get a little bit more advanced with the intersection over the union. So you can't just say, is this a cat or a dog, yes or no? Calculate precision and recall. You kind of have to say, how well is this box? Even if you predict that this was correctly a cat or a dog, if you don't have a good box to wrap around it, it doesn't really help you that much. So you kind of have to use the ground truth of that box with the predicted box and see how, and then you run a intersection over a union to see how tight the overlap is between the two. And if you have an acceptable overlap, then you go ahead and calculate the precision if you predicted the right class.
Great. Cool. So that's all on questions.
Okay. So I'll quickly do a segmentation. So this is a little bit more of an advanced approach. And, maybe I could show, I think I did run this notebook. Here's just an example of it working. I'll share this notebook, but it's super cool how you can pick any image you want, based on your training set. And let's say I pick this really nice picture of a bathroom, and you choose, it's important for you to choose the data set that it is trained on, as well as the network, the model. So it's kind of two choices. What type of data was the model trained on? And then what model do you want? Do you want a model that's, going to get you really high accuracy, but is kind of slow, or one that's kind of fast, but not as high accuracy? So this one that I chose was run on a furniture data set, and it's slow, but it has higher accuracy. So when I run this on the bathroom, you can see how well it detects everything. It detects the mirrors really well, detects the toilet well. Kind of messed up here. I think that was, I said that was two different things. Maybe it kind of recognized maybe the inside of the bathtub, but overall it does pretty well. I'll share this notebook. You can, try other images of living rooms and bathrooms, but here they are both together. So that's really what segmentation is where it's not different, where it's recognizing boxes. You're trying to perfectly, segment around the image. Much harder problem, also harder to create training data for it. But if you are able to train, a good segmentation approach, it's super powerful. Something like, painting walls, you definitely need to have a segmentation approach. If you say something like, I want to match this table lamp, I'm in love with this table lamp, you might not need segmentation. Object detection might be good enough. But it just really depends on what your goal is and what you're trying to do, and whether it's worth it to create a training set. I just put in this graph just to kind of show you how many different models there are with segmentation, which is, kind of crazy, just how much this has evolved. The very first model is the one I'm going to talk about that did segmentation, but there's all these different approaches to improving this. It's gotten crazy how accurate all of these are, and they have gotten really complex. But I don't know, it is kind of nice when you kind of learn how maybe one of these more complex models work, and you're like, you know what, it was all worth it, because it's not like they were just doing it to be fancy, because you get such a higher amount of accuracy with all these, different approaches, with all these, different models that have been created. But I'm just going to focus on this one, the FCN model. And here's just another timeline. These, all the equations, I know that a lot of these equations look crazy, and a lot of these names and concepts can be overwhelming, but kind of use this presentation as just kind of a reference to keep going back to. Don't, it takes a long time before you feel, pretty comfortable with all this. And I don't want you to feel like this is kind of, don't feel overwhelmed. It definitely takes looking at this over and over again before you kind of get a good handle of it. So let's just kind of, here's a fully connected network. So what you're basically doing to be able to do segmentation is you remove what I talked about in the beginning of the talk is the fully connected network. You're basically removing that. And that's really nice, because then you can have these images be any size, because the fully connected network is kind of like a set size. And once you get this to go through something that is, you change everything and you say every single layer is going to be a convolution. And when you do that, then you do this thing called upsampling, and it upsamples the image from these layers right here. So the way this is I know it's crazy, that this is one of the simplest models for segmentation, but what's basically being done is you take this thing, same exact thing that we're building on, convolutional neural network, VGG16, same thing we've been talking about. You just make a few little changes to it, and you can basically, you have a segmentation model, which is pretty cool, because if you learn how VGG16 works, then you can, do a lot of cool things with it. We use that for the SSD model and object detection, and we can use the same exact, CNN for segmentation by just doing a few changes. So what happens is you're extracting information from the later layers. So you have pool 3, pool 4, pool 5, which are all, right here in the later layers. But the problem is with doing this is, let's say I just extract from this layer, pool 5. Pool 5 is, I think that's around here. When you upsample it, you have to upsample that to get back to the original image 32 times. Now, why even go to the last layer? Why not just go to pool 3 and then do an upsampling? So I only have to upsample, by 8 times. The reason for that is, I think it might take a little bit too, it might be hard for me to go all the way back to the original slide. But if you remember how the lower layers have very basic features, where the convolution is learning edges, the features are lower layers. They're not very rich features. So so even though I still have a lot of spatial information left with pool 3, these features are not as rich as when I go later. So what happens is if I just use the rich features and I lost all the spatial information, look what happens when I do that segmentation. You can't even tell, whether this is a biker or not. It looks like, 2 blobs. But then if I say, okay, I'm going to go to pool 4 and only upsample by 16 times, and then combine that with my pool 5 that has the richer features. And then I combine these two and I upsample 16 times, you can see how much better the segmentation is looking. And this is the ground truth, by the way, to the very right. And if I do the same thing, I upsampled here, then I go back to pool 3 and I upsample 8 times, yeah. So I take the pool 3 and then I combine that with this previous approach, the 16 times upsampled, combine those two, and then 8 times upsample it. I've got the best of both worlds because I still have the spatial information. I still have the richer features from the later layers and the spatial information from the earlier layers. And you can see how much closer that's getting to the ground truth. So very cool idea, the person that did this approach. I think this came out in 2014. And this was the first thing that, really started doing deep learning with segmentation. These segmentation approaches get a lot more complex than that. But if you kind of start off here, read this paper and kind of understand it, it's almost all other approaches are kind of built on this idea of combining layers and upsampling. Really quickly, just to talk about upsampling, it's basically like, a lot of people call it a deconvolution, but it's really not. It's like if you do a convolution and a deconvolution, you get the same thing. They're inverses of each other. Upsampling doesn't really work that way. You're basically taking a very small layer and you have a filter that you're multiplying against it. And as you keep, rotating, you get all these different values. So you can see how that's bigger than this. So that's how you kind of go from a small layer to a big layer, is you have a small filter, but you rotate all the way around. And yes, there are blank spaces around the edges, but when you do that with these weights you learn, you go ahead and upsample. Only thing that I'll talk about, if you do choose to be a practitioner in segmentation and want to really kind of learn about the more advanced approaches, there's this other type of upsampling that's really kind of exploding as far as getting higher and higher accuracy. Is you can see how much is lost when we remove these fully connected layers and you're adding more and more convolutions. There's hardly anything left. Look how small these layers are getting, and you lose so much spatial information. So there's this other type of convolution where kind of, instead of going like this where it's really tight, it's called an atros convolution where it's more spread out. So it tries to retain the spatial information as you go all the way through. Very last slide. Here's just different results of different data sets. So FCN is the approach that we just talked about with segmentation. IOU 29.3. This is the furniture data set that I just showed an example of. You can see how that's 45.9, which is state of the art. And the backbone, that's just the convolutional neural network. With the example I showed, that was using VGG16. And you can just see how much better it's getting. It's just incredible, everything that's kind of going on. Cityscape data set, same thing, FCN, the approach I just demonstrated, 65.3. And you can see all these different approaches. And this is from a survey paper that I can share, which kind of, if you really want to, get deep into this and really understand all the different segmentation approaches, it's incredible, how far this field has, gone from this, and this is only in a 5-year period with segmentation from intersection over union. That's what IOU is. It's gone from 57 to 83. Very last one, Pascal, another data set, 62. And I believe that this is state of the art right now. And you can actually run Deep Lab v3 really easily. There's TensorFlow Hub where you just go ahead and download the model and you can run it. You don't have to train all these, models from scratch. You can just go to, there's a TensorFlow Hub link or PyTorch Hub link, and you can just, download these all pre-trained, which is pretty cool. 89.0 on this data set from FCN, the one I just presented. 62 score was FCN with the VGG16. And then it goes all the way to state of the art that's at 89.0 with segmentation. So that's really it. Those are the 4 different approaches, traditional computer vision, classification with convolutional neural networks, object detection with detecting bounding boxes, and then going all out with segmentation and wrapping around, different things you can detect in images. Any questions, Brian? I can stay as
let me check the chat window. Nothing there. I mean, nothing right now. If there's any questions, I guess I'll give it another second. But man, this is good content.
Awesome.
This is awesome stuff. I all through the chat window too. You have a lot of people, messaging who had to jump off a little earlier, saying thank you and how much they've learned. So.
Oh, that's awesome.
Great.
Yeah, just super happy to help. I know it's definitely tough to go to conferences now, so just wanted to thank you all, again, for just giving a really great outlet to, with the data science development series.
Yeah, absolutely. And we'll make sure that all the content here was shared out. We have a Slack channel where we'll make sure Matt joins, Jing from last week joined. We have some, my entire data science team from Pandera Systems joined. So we want to open up a dialogue and a channel for people to be able to communicate, share ideas, ask questions. And that's what we're going to be using that Slack channel for. We will also be posting all the content you saw today into that Slack channel and any additional research papers that Matt has mentioned, et cetera. But yeah, I mean, I learned a lot. I will admit, computer vision is not my expertise, and this is like this is eye-opening stuff for me too. So I really do appreciate it, man. This is great.
Oh, no problem. Yeah, it's definitely an awesome field, and I mean, a lot of things I didn't even know were possible before I kind of just started off with doing visually similar, and then as I read more, like I was like, gosh, I can't even believe like you can actually recognize items of furniture and images automatically, and then, it just seemed like, I don't know, I think I see screenshots, but until you do it yourself, you're still like kind of doubtful, like you can't believe like this stuff actually works, and then you go ahead and train it, and then it's pretty incredible. All these things are.
Absolutely. And I'm glad you mentioned the TensorFlow Hub and the PyTorch Hub as well, because what we showed today was a lot of math and it could be overwhelming, but like there are a lot of smart people out there that are sharing some of the work they have done. So, definitely check out TensorFlow Hub or PyTorch. And you could actually put this into, start actually playing around with it today. Not really having to know the deep mathematics behind it, right? So.
Yeah, absolutely. Don't feel overwhelmed if you see the mathematics. It can be helpful to kind of know, should I use this model or that model? But if you actually want to do this stuff, at the company you're working at, and someone says, oh, wouldn't it be cool if we could do some segmentation? And you look at all the math behind it, you're like, there's just no way I could do that. It's not, it would take forever. It's not true. With TensorFlow and PyTorch Hub, I'll share a notebook for doing it, but it's like, 20 lines of code to get DeepLab v3 running. You just download the model and you create the image, and then it's incredible. It just runs the segmentation right away.
Yeah, absolutely. Well, with that, I appreciate, there's still 75 people on, so I appreciate everyone staying over about 30 minutes here. I'm glad everyone learned a lot. The content was great. We'll make sure to share it afterwards. So everyone else, with that, have a good night, and we'll see you next week.
Thanks a lot. Really appreciate it.
All right. Thank you, everybody.
Thanks.